Okay, good morning everyone. So we will continue to focus on the fundamental of the metal oxide semiconductor field effective transistor. So we will today we will start to talk more about this MOS transistor. So last week we have briefly discussed the MOS structure under the positive and negative bias, and now we can also use the Venn diagram to analyze the case that are under the different bias condition. So first of all, we have the case that where we can apply as what we normally call as a flat band condition, which is generally have the structure as a Venn diagram. So if you have to draw the Venn diagram, where this is silicon, and we have the dielectric, and as usual we have a conduction band, valence band, and since we consider this is a MOS structure on top of the p-type substrate, and therefore our Fermi energy will be close to the valence band. And at the condition that our band of the dielectric and also the Fermi energy will under with the case of a flat. This is condition that we call as a flat band. So the voltage that can cause this flat band conditions we call the flat band voltage. So this is what we normally call as a flat band. The energy band, so based on the name, that means that the energy band is flat. Because originally the band could not be flat because of due to the we have the different metal work function versus semiconductor work function. So originally the band would not be flat, but if we intentionally to add a certain bias that cause a flat energy band, this is condition we call the flat band voltage. So once the energy band is flat, that's indicating that no charge exists in the semiconductor. So since this is not your first time to use a Venn diagram as a tool to analyze the semiconductor physics, so you should realize that as long as there's a band banding, that always suggests that there's a charge, there's an electric field, there's a potential drop. So as long as we have the flat band, that means that there's no any charge existing in the semiconductor under this condition. So now we can consider as two different cases. The first one is we apply the negative voltage. So this is a negative voltage applied. So based on this condition, conduction band, valence band, and our Fermi energy here. And because now we apply the negative gate voltage, so in the Venn diagram, once we apply negative gate voltage, which means that we will try to increase the difference between the gate voltage and Fermi energy, and therefore we will have this bending upwards So we will have this band bending upwards. That's because of negative bias here. So with this consideration, we will start to see also the band bending in the semiconductor interface. And if you look closely, you will find out that this is a region where we start to have our Fermi energies here. So now you see in this region, this is region of Fermi energy is getting close to our valence band. So this suggests that we start to have getting more holes in this region. So that's why we have hole accumulations. So this understanding is very consistent to what we have been told last week, that once we give the negative bias, we always have the whole accumulation. So we can either use the way where we explained last week, but we also can use the way using the band diagram. For sure that in the future we will prefer to use a band diagram because that's a very simple schematic, and then it also can be considered as a universal tool to take into account all of the cases, not only for silicon but for all kinds of semiconductor. So this is a case under the positive, negative voltage applied. But on the other hand, if we have the positive voltage applied, so if we have the positive voltage applied, so similar analysis can be done with, we consider conduction band, valence band, and our Fermi energy is somewhere here. So that's our Fermi energy here. So once we apply the positive bias in the band diagram analysis, which means that we will have the lower voltage compared to the Fermi energy. So which means that now we try to pull the band diagram as a downward. So in this case, which means that in the surface, we can foresee, the downward as well. And this downward also suggests that our Fermi energy here is getting close to our conduction band. And therefore, that will be depends on the how far or how close of our EF close to our conduction band. So if in the case as a little bit far, if we have the case probably like this, so therefore our conduction band is now falling below our Fermi energy. So in this case, we will have the induced space charge here. especially this is induced negative space charge. Because right now we have our Fermi energies close to our conduction band, and this induced space charge with the such depth, which is our depletion width. Okay, so this is the previous slide talk about the bias under the small gate bias. But if we try to apply as a sufficient large positive bias, and therefore we have invert the surface of semiconductor from p-type to an n-type semiconductor. And this means that if we try to draw the band diagram again, if we try to draw the band diagram again, and now we apply sufficient larger of our gate bias, so now if we have a sufficient large gate bias, which means it can have a chance that this conduction band can fall below our Fermi energy. So once this conduction band fall below our Fermi energy, that suggests that we have the very high electrons can exist in this region. So that's why the text say that we have inverted surface of semiconductor from p-type to an n-type semiconductor. Which we normally call this as an inversion layer. So now we have created an inversion layer of electron at the oxide semiconductor interface, which is shown in this region. And this is a case under the large gate bias. So the same analysis not only can be considered in the p-type substrate, but also in the n-type substrate as well. So if we take into account as an n-type substrate, then actually we'll try to have the different, completely opposite consideration. For example, once we apply the positive gate bias here, and once we have a positive gate bias, our Fermi energy was getting more close to our conduction band. So that will have the accumulation of electrons. So that's with considering of the n-type substrate. But also once we apply the negative gate bias here, we will see our Fermi energy here is start to a little bit close to our valence band. So that creates a induced positive space charge region, and therefore this is a region where we consider as a space charge region. And finally, we have a large negative voltage here. And therefore, once we have a large negative voltage, we will see this Fermi energy is below our intrinsic Fermi energy and then it's close to our valence band. Once it's more close to a valence band, that means we have the Hall inversion. So in this case, we will start to have the Hall inversion. So that would be inversion layer of holes. So that's the same idea that how we analyze as for p-type substrate. So the next questions we will be interested in is that how do we determine this depletion layer thickness, which is also the space charge thickness, which is XD here. So this is a case we consider as a p-type substrate and under as a small positive bias here. And with this consideration, we have the two different parameter. One is what we consider as a phi s, which is a surface potential. And therefore, first of all, the potential phi half p is a difference between the EFI and EF. So therefore, we can use the equation that where we already derived a while ago, that the phi fp is equal to Vt natural log of doping Ni over Na over Ni. And then we take into account the phi s, which is the surface potential. And also, the space charge width can now be rewritten in the form similar to a one-sided p-n junction. So therefore, we can borrow the equation that coming from this one-sided p-n junction and put in here to estimate the space charge width, and therefore we have the result XD is equal to this one, 2 exon s phi s E Na. So basically, we just borrow the equation where we already have, and we just apply those equations to the case that in here we consider this is a depletion in the p-type semiconductor, and then we take into account as a one-sided p-n junction. And next, if we continue to increase bias, and then we for sure will see this EFI will getting more lower than EF, and therefore there's a condition where our phi s, once the surface potential is equal to 2 phi fp, and then normally we consider this is a very critical condition that we call as a threshold inversion point. And then the gate voltage that creates these conditions, how we call as a threshold voltage. And this is exactly the condition that if you look at our typical ID versus VD characteristic. And once we start to apply the bias with a certain condition, once bias is larger enough, then we will start to see the current flowing here. And this condition is exactly we call as a threshold voltage, VTH. So the next question is that how do we analytically to determine the threshold voltage? For sure, for the measurement experiment, it's more easy to define. As long as the current increase, we can just define as the threshold voltage. But we will be interested in that what would be the condition what would be the analytical equation that can analyze this threshold voltage here. So once the VG that create the phi s is equal to 2 phi fp, which also means that your Fermi energy here is much close to the conduction band, and therefore this is a condition that we consider to create as enough inversion layer that current can increase. The electron concentration at the surface is an exponential function of the surface potential. Therefore, the NS, which is the electron concentration at the surface, normally is proportional to exponential of a phi s. So therefore, a little bit increase of phi s that can cause a huge increase on our surface electron concentration. That's why we can see the dramatically increase of a current here. The surface potential may increase by a few kT volt, so we can increase a few volt, but which will change the electron concentration by order of magnitude, but the space charge width changes slightly. So which means that at this condition, actually the additional VG will apply here will mainly reflect to the result of the surface potential in the end to increase the NS, and therefore the depletion width, the charge of depletion width here will not increase anymore because of most of the charge will be induced in this region because we increase the charge exponentially. So as long as you increase additional bias, you will see the additional generation of the charge here rather than continue to expand the depletion width. So that's how this sentence try to illustrate. So in this case, the space charge region has essentially reached a maximum width. So again, just let me illustrate again. So once we reach this condition, additional VG, any additional gate bias here will only cause the NS exponentially increase. And therefore, this, to consider the charge balance here, you apply the positive bias here, you get the most of the charge will be reflected on this region. So therefore, it means that the charge in this depletion region won't change anymore. So if the charge in the depletion region, in the space charge region won't change anymore, that means this will reach as a maximum width. So by consider these phases, so now we can put the phi s equal to 2 phi fp, and now we can estimate the maximum depletion, the maximum space charge width, as shown here. So for the same analysis, we can do it again on the N-type substrate. So again, we consider the N-type substrate, so we just apply the negative bias here. And once the negative bias is negative enough to reach the condition of the phi s equal to 2 phi fn, and therefore we can still define as a phi fn is equal to Vt natural log Nd over Ni, and as the same, we can estimate the maximum space charge width in this case because of this additional. Similarly, the additional Vg this minus delta Vg will only will reflect this as an exponential increase of the whole concentration. So this will mainly cause exponential increase of the whole concentration, and therefore we will still reach the maximum width of the space charge width here. So this is a case for the N-type substrate. One thing is very important to remind is that when we talk about the, no matter for NMOS, PMOS, we always try to look at together to have a side-by-side comparison that where we have ID, VG. So in the case of the P-type substrate, we have the electron inversion in P substrate, and therefore we can have the curve something like this one, and therefore we define this as a threshold voltage. And because this is an electron conductive, and so we also call this as an N-channel MOSFET. So therefore we just call as a NMOS in brief. On the other hand, if we consider the case where we have the whole inversion in N substrate, so therefore we will foresee to see once we give enough negative bias, we start to see the whole current here, and still we can define this as a threshold voltage. And because this is a whole conductive, so therefore we normally call this as a P-channel MOSFET. And we call as a PMOS in brief. And since the surface potential and also the surface charge density, the inversion that causes this very high density of the inversion charge in the surface, that we also call as a surface charge density, is one of the key parameters that we are interested in. So for sure that we will spend some time to analyze this surface charge density here. So let's back from the one fundamental equation where our N is equal to Ni exponential EF minus EFI over KT. So that's our very fundamental equation here. And now we have Ns can be considered as the original phi FP plus now we have this additional phi S. So this additional phi S is mainly due to the applied bias. So once we have this equation, so then we can have this one, and we divide this one as a two independent term as shown in here versus here. And also if we try to define this one as a constant, and therefore we have a result of Ns is equal to NST exponential delta phi S over Vt. And this equation is very important because it shows us a certain fundamental increase of how our gate bias, which is the surface potential, in the end influence our surface charge density here. So this equation suggests that if you look at this is Ns versus our phi S here. So as long as we increase as a 0.06, which is equal to delta phi s equal to 60 millivolt. So as long as we have additional 60 millivolt increase in the service potential, ideally we should have the NS increase by 10. So the inversion charge density increased by a factor of the 10 with a 60 millivolt increase of the phi s. Of a phi s. So this is a very important conclusion. That means that as long as we just try to get a little bit, only 60 millivolt increase of the phi s, plus a 60 millivolt, which is very small amount of bias. Ideally, our service charge, our inversion charge, our electron concentration in the service should increase by factor of the 10. This result also lead to as a one fundamental bottleneck for our transistor. So if you try to consider this concept and transform into a current versus a voltage, which again we plot as a log current versus a gate voltage. So anyhow, the phi s is proportional to our gate bias, and our NS in the end will correlate with our drain current. So the correlation between the NS phi s in the end can be also transformed as more important for what we are normally consider as ID VG curve, because ID is proportional to a phi s, and then the VG is proportional to ID is proportional to the NS, and VG is proportional to the phi s here. So in the end, this correlation can be also transformed to the ID versus VG. So based on this correlation, also suggests that if you try to analyze the base case where we should have is additional VG. If we have additional VG equal to 6 millivolt, then our current should increase one order. We should have the 10 times higher drain current. Right? So that's the same. It's the same conclusion from this equation, but now we just extend to the case we are more interested in as a ID versus VG, and that's also in the end cause as a fundamental limit that because of the log ID versus VG can be also considered as one of our most important figure merit, which is our subthreshold swing. Which is the slope of a log ID versus VG. and that's normally we also call as a SS. So therefore, you will be very often to hear that the best case we can achieve for the transistor is 6 millivolt per decade. So how this 60 millivolt per decade is coming from? Actually, it's just coming from this very fundamental equation. It's nothing very complicated. It's very straightforward. And then if you follow from the beginning, you should also easily to follow the understanding here. So that's cause this as one of the main goal that everyone who work on the transistor, no matter what kind of transistor, we always try our best to make it as close to the 60 millivolt per decade as possible as we can. But unfortunately, it's very difficult. So therefore, you look at the paper that I share for the TSMC that published for the 5 nanometer, 3 nanometer, they always highlight that they can make it as a 70 millivolt per decade, which is already very good, but still can be improved. Still, we want to improve as close to 60 millivolt per decade. But once in the future, if we really can make it as a 60 millivolt per decade, that causes another issue because this becomes a fundamental bottleneck, which means that we cannot make a transistor even better because this is a fundamental physics. There's no chance to break this physics as long as we need to create a new physics. We need to create a new device operation physics. But it is indeed that in the semiconductor community, we have some very interesting technology in the end can be possibly to break this fundamental rule by taking into account additional physics, by taking into account additional understanding, by using a novel materials that create as a novel physics, and in the end we can break this rule. But in the end, still 60 millivolt per decade is general as a target, but also limit for the most of the CMOS transistor. So now, when we discuss as a metal semiconductor, we have been already talk about there's a sense between the work function difference. So in here we also have this work function difference between the metal, oxide, and semiconductor. So this is a energy level before the contact. So we have the semiconductor here. We still have an electron affinity, and this is our SiO2, and then this is our metal work function. And once we put those together in the thermal equilibrium after the contact, then we will see that there's start to have this band bending in somewhere here. And this is because of the metal work function and the semiconductor work function will not be the same. So we will start to see this kind of a band diagram. And also, in the case with MOS system that didn't apply any bias, we already see a little bit band bending here. So that's why that in the several slides we mentioned about that we can intentionally to apply the certain bias to make this as a flat, and that's we call as a flat band condition. But if we don't apply the flat band condition, originally there could be the band bending if we just put the metal oxide semiconductor together. So now we'll start try to do the analysis, try to analyze this work function difference here. So we have this VOX 0, which is a voltage drop. This is this one. The voltage VOX0 is a potential drop across oxide for zero applied gate bias, and it's not necessarily zero because the difference between the phi m and electron affinity. So because of our metal wall function and semiconductor wall function will not be the same, so in the end you will have this voltage drop VOX0 here, which is cannot be avoided because of we will have a different phi n and the electron affinity or semiconductor wall function. So now we define as this one phi n prime as a modified wall function, and chi prime is a modified electron affinity, and with the consideration of the everything put it in the left hand side, metal wall function plus this voltage drop, which is E phi m plus E VOX0, that would be equal to everything on the right hand side, which is electron affinity plus half band gap, but minus E phi S0, but again plus a phi FP. So just let me write the result first. Electron affinity plus half band gap minus E phi S0 plus E phi FP. So if you try to look at in the right hand side detail, you will figure out that this is true because of this one plus this one and minus this one and again plus this one, because this minus this one will be equal to this. So in any way it will be equal to these two here. And now we try to do as a subtractive. So we subtract here. So if we do the subtract here, so now we have the modified E phi Fm plum plus E VOX0 is equal to E chi prime, and the rest is a set. So again, we just try to move everything. The phi S0 plus E VOX0 is equal to minus phi m prime minus and then in the end we just define this term as a phi ns, which is a metal semiconductor work function difference. So one more small reminder is, as long as we found out the band is not flat, that means that the surface charge are already existed. So the same is we can do on the N-type substrate, and then we also able to calculate the phi n s. So this calculation is not that a big deal. Just try to base on, as long as the band diagram is corrected, and as long as you put the parameter, the phi fn, evo s, electron affinity, loss definition are corrected. So it's just a matter of the left equal to right, and then you can always get these right calculations. And there's an additional one concept is that we consider, in most of the case, in nowadays, if we look at the gate electrode, so we have several possibilities. In the early time, we mainly use as a polysilicon with the doping. So we consider N plus, P plus polysilicon. And recently, of course, for the advanced technology, we will start to use a metal gate. So therefore, we also have to take into account that if we use N plus, P plus polysilicon, that means this is a material that's still considered as a kind of the semiconductor, but this one will also create as a different band diagram. So the degenerative, that means a very high doping concentration, can be considered as a gate as well. So if we consider the doped silicon, polysilicon, then you should also consider that in the metal side, we have this kind of the band. We still have the valence band, we still have the conduction band, but just because this is a degenerate type, so that means our Fermi energy is equal to our conduction band. And this is a case for the Fermi energy equal to the valence band. So that's probably is not that critical as nowadays, but for some of the technology we still use a polysilicon gate. Then you should also be aware of that we have this consideration. So once again, now we got more clearly about the case that how do we analyze the band with the considered MOS structure. So now finally we should be able to have the way to more clearly to estimate the flat band voltage. So the flat band voltage voltage is defined as applied gate voltage such that there's no band bending in the semiconductor, and as a result, if there's no band bending here, that means that there's a zero net space charge. Zero net space charge in this region. So the bias with this kind of bias that causes the flat band is we call the flat band voltage. And no bending, that means zero net space charge. So in the previous, we have already derived this equation. If a gate voltage is applied, the potential drop across oxide surface potential will change. So now our VG will be considered as a delta VOX plus the delta phi x. And this one, delta VOX, is originally an additional. That will cause this is mainly due to the additional bias, and also phi s can be considered as originally and then after the bias here, and with this and this is exactly as a phi s. So now our VG is equal to VOX plus a phi s plus a phi s. So now again, we're back to the very similar analysis that we have been done in the PN diode. We always starting from the very basic. If you try to follow the previous, if you already follow the previous section, so the MOSFET analysis, MOSFET or the MOS structure is based on what we have been learned from the previous. So the analysis styles are very similar. We still have to take into account as a charge distribution, but now we just have to consider the charge distribution not only as a P and N, but it's actually the metal, oxide, and semiconductor here. So now we assume they probably have a certain amount of the surface charge in the oxide. That's very typical for the typical semiconductor. During the process, we always possibly to induce some non-ideal charge, which can be fixed charge or whatever that in the dielectric in the silicon dioxide. So in this case, we assume a certain fixed service charge. In the oxide. Because the silicon dioxide is not perfect, so it could already have a certain possible charge here. But now we assume this is a positive charge in the oxide here. So to make sure that we have a zero net charge in the semiconductor, so ideally that we should have this as a zero net charge in the semiconductor. That's how we call the flat band condition, right? So in this case, that means the charge that we apply from the metal should be equal to plus charge here. So this is a QM prong, and this is a QSS prong. Because for the charge neutrality, this is a zero, which means this plus this will be equal to zero, and therefore you get this equation here. And we consider the Qn can be estimated from here, and Qs is related to the inside the oxide here. So in the flat band condition, the surface potential is 0 or phi s equal to 0. So therefore, this is 0. This is the equation coming from last slide. And then this Vox is equal to minus QSS prime over Cx. So in the end, our flat band condition VFB is equal to phi ns minus QSS prime over Cx. So the flat band condition is determined by metal semiconductor wall function difference and also the surface charge in the oxide. That will determine our flat band condition. Again, the calculation that the analysis here is not that complicated, but just one easily confusing is that we have many terms here. We have a QM prong, we have a QSS prong. That's also sometimes cause confusing. So that's something that you need to a little bit have a patience about this. So with this analysis, we can start to further explore that how do we get the threshold voltage calculation. So the threshold voltage is defined as the applied gate voltage required to achieve the threshold inversion point. And again, we assume that there's an equilibrium oxide. We can still use a charge distribution. This kind of analysis helps us to understand Still, we assume that there is a service charge in the oxide. Now, as you still remember that to estimate the threshold voltage, actually it's a condition that we reach as a maximum depletion width. So once we apply the bias in the metal side, we will start to have this charge here, where we call as a QMT plumb, Q metal threshold hole. That's what we call the QMT plumb here. And if you just recall the previous analysis that we increase getting more and more bias, and then in the end we should to reach the condition. Before we reaching to the threshold hole, we first will reach the maximum depletion width, right? First, this will continue expand until on the one critical point we start have this threshold voltage. We start to have this inversion charge, where we will see the very higher electron density here, and therefore the condition to estimate threshold voltage, which will be the condition that this reach to the maximum width, right? Because beyond this point, we start to have this NS generated. So therefore, with this consideration, to estimate the threshold voltage, we will consider as our space charge width reach to the maximum point. So therefore, this is a total charge in this space charge region. Because once beyond this critical point, we will start to see very high inversion charge will be generated and inverted in this region. But this is threshold point, so these things haven't happened. So therefore, we consider as this as a criteria. And therefore, the QMT plumb, based on this charge distribution, the QMT plumbs plus the QSS plumb will be equal to the QSD plumb max. And also, the charge in here, that will be very easy to estimate if you just remember how we do it in the p-n junction, just equal to this times the concentration here. So therefore, the QSD plumb max just equal to our NA(x) dt. So, furthermore, move to the next step. We consider the previous equation that once we apply a certain bias will drop in the oxide, and certain voltage will drop in the surface. So therefore, this term, which means the voltage drop in oxide, and also this one is a voltage drop in service. So at the threshold, we can define Vg is equal to the Vtn, that's a threshold, where Vtn is the threshold voltage that creates electron inversion layer charge. And therefore, with this consideration, now we change Vg equal to Vtn is equal to Vox at the threshold point plus the 25Fp because now our service potential, if you look at the previous what we defined, the threshold voltage is a condition that the phi s equal to 25Fp and plus a phi ns. And also, the Vox can be estimated, can be related to the charge on the metal and to the oxide capacitance, and therefore we have this term which can be equal to this one. So right, this is something, this plus this is equal to this. So now this Q and T can be estimated by this minus this one. So again, we just put everything inside this term. So we get this one. And finally, this is equal to the phi VFB. So finally, we have the VTN can be estimated by considering the phi FP flatband voltage and also the maxima, the charge in the maximum depletion width condition. And once we understand the MOS, the basic MOS, and how to analyze the threshold voltage, so the next is we are interested in as a capacitance voltage characteristic. That's how we normally call as a CV characteristic. And when we do the CV characteristic analysis, you have to first to understand a little bit more about how do we perform the CV measurement. So when we characterize the capacitance versus voltage, it's normally considered as we have the voltage in the time domain, and then of course we will try to give us a DC bias. But one of the things more unique for CV is that we will give one additional AC bias on top of this DC. So you will see with a certain DC, you will see as a up and down AC signal on top of this DC. And this up and down additional signal that will cause amplitude difference. At this region, we might have V plus dV. At this region, we will have V minus dV. And this plus and minus dV will cause the charge difference. So at this point, we will have the charge difference. We will have the charge difference here. And with this consideration, we can start to consider to characterize the CV because the CV capacitance is mainly related to the charge. So now, again, we're back to the first case with the negative bias. And then we also use same charge analysis here. The whole analysis is also very similar to the case we talk about PN junction for the CV. So we have a metal oxide P-type substrate here. And because right now we apply the negative bias, so we can consider the negative charge in the metal side, minus Q, and positive charge on the substrate for the charge neutralities here. Now we have the additional AC that will cause this decrease of the delta Q, and that will reflect at this region. This contribution is mainly coming from this DQ prong, which due to our AC signal. So with this consideration, we have a DQ and DQ here, and therefore we consider this DQ, then we will have the capacitance between these two DQ prong. That will be exactly equal to our oxide capacitance, which can be estimated, which have to consider the oxide thickness and oxide dielectric constant. So therefore, if you try to plot the CV curve, CV, and under the negative bias condition, you get a flat capacitance C at the accumulation region, which is equal to Cox is equal to A zone Ox over Tox. That's all. So it's very simple. It's not that difficult. Just under negative bias, in the end, we figure out that the accumulation capacitance is exactly equal to our oxide capacitance. And now the next is we for sure will be interested in continue to increase the bias and to understand how this CV characteristic. So with the next condition is we start to consider there's a small additional bias. Small positive bias. So we consider this small positive bias, then let's look at again for our charge distributions. So we have a metal, we have an oxide, we have a P-type substrate here. Now we give us a small positive bias. to maintain the charge neutrality, for sure that we will start to have the negative bias induced in this region. And we consider this is a condition that we start to have the depletion. So therefore we define this dash as a XDT. And now we put as an additional AC signal. So the AC will cause additional decoupling. But now because we try to have the space charge region, depletion region in the substrate, you can see from this Venn diagram, this Fermi energy just start to fall away from valence band, but haven't beyond our intrinsic Fermi energy. So therefore, this creates a depletion region here. So any additional decoupling just become as an additional decoupling in the end of our depletion region. So therefore, with considering the CV characteristic now, which will be equal to Cx, but also in series with this depletion width, right? Because now we have a decouple here and here. So that must be the capacitance of this one and this one in series. So therefore, under this consideration, this is condition we call as a depletion. Why we call depletion? Because now we are actually make the P substrate in the depletion, which is equal to Cx plum plus CSD plum. And the rest of the calculation is very easy. This is I would say just a elementary school calculation. So this, and then because now we have a CSD here, which should be related to the depletion width XD. And then with once we continue to increase the bias, for sure that will be reached to the maximum depletion width. And therefore, the maximum depletion width, that means that we will cause the capacitance decrease to the minima. So, in the last operation, we have this C accumulation, right? But now we keep increasing the bias. Our depletion width is actually increased. This is getting deeper, wider, and wider. So therefore, our capacitance is getting decreased and decreased. So we will expect to see like this one. Because our depletion width in the substrate is expanding, but this will expand to the one point that the depletion width will reach to the maxima. And once the depletion width reach to the maxima, which will be the case of the minima, right? So this is a capacitance at the minima, which is equal to the maxima depletion width. So this is a depletion capacitance. Okay, so we will stop here and come back later to continue for the CV characteristics.就要少3份，其中那个2份，对，那少2份，然后拿去，然后你们印完谁进来，就进完后我们就直接发好这边，我先帮你正完，然后等他们问再发。对，我们会改成那个我跟怎样讲？对，所以我们会改成
90分的70
对，我们改成今天晚上。
这样子。
对。
那题目这也要给吗？他说反正里面都有。
没关系，那我们就约通常
70几的，
对，就我会给线上，然后就晚上10点半。
可是我觉得50几的，因为50分以下的就37。我也是想要知道。啊好。因为我想说30几比较难找，50几啊70几啊
70几分中间吧。
对啊。
这是哪一个系？
为什么？
这边一个9。2个系。
对，2个系。这样。
成功。
那你们等他们印完就可以直接拿来，我就会提早发考卷，考完就交给你。好。就大概我想花大概现在印差不多半小时，
对，
所以我大概11点半、11点40发考卷。
11点半，好 OK。
Okay. I'll try to do this. Sure. So you're from ECS actually? Yes. Okay. Where are you from?
Sarawak.
Oh, but why you don't try to ECS?
I guess
But from the someone you have the or is the Mandarin name named by the
I guess not.
Oh, okay. So your parents, one of the parents.
My father's side.
Oh, okay. But Saudi is a country that we have the diplomatic before us.
4 years now.
Oh, but it's in the South.
So America.
Oh, okay. Okay. It's nice to know you. So
I apologize for this time.
yeah, try to think about it. I think probably you can do this. Yeah.
Yeah, I think it's fine.
OK，
CV
对，
就是为什么在那个 accumulation 的时候是往上还是往右，但是在 depletion 是往右，然后又回到这边的时候，回到 inversion 就是往下回击。
哦，正常来说 depletion 的时候，因为它会是你增加这些会造成你的这个的宽度 depletion width 的宽度的增加，就它就是就像你的 CV 是往下增加，没关系，就是你的宽度变宽。所以它这边是会让你的这个宽度会达到一个最宽，所以你才会有 C depletion。那其他就直接反映在它的这个 accumulation 的这个，你的 x 轴是你的 density， 对，所以它就直接反映在你的 density 上面，对，它不会反映在你的宽度，只有在 depletion width 的时候，因为这边是宽度改变了，因为你是偏压，它会一直 deplete， 你 deplete， 所以它就宽度会一直变，对。
所以它这个 XDT 其实是最大的是指红色的地方。
因为通常 DQ 方式，它那个 charge 是没有人在估算那个宽度。对，因为 DQ 就是一点点。对，通常你的 CV 的反应就是这个的之间的距离。
好的，谢谢。
等一下会发，
因为我们也要赶快提交。
等一下会发，我要一个一个发回去。 Okay, so next we will move to the last mode, which is the inversion mode. So in this case, we apply a large gate bias. We apply large gate bias here, and then again, if you look at the charge distributions, so we have the metal, oxide, and also the p-type substrate here. So now we have the positive bias. And then in the end of the depletion mode, which we described in the last page, is that we have this charge in the depletion region. But now, again, because of now we reach to the maximum depletion width, and then the further bias will just induce the very high density surface charge. So therefore, the additional bias AC signal that will cause this DQ plumb, which in the end will reflect in this inversion charge. So now, again, if we look at the CV, which will be back to the oxide capacitance. So therefore, the CV characteristic from the left, the most left hand side, we have the accumulation, and then furthermore we have the depletion, and then the last one we have this inversion, and this inversion capacitance will be just equal to our oxide capacitance, so which in the end will be exactly the same like our accumulation capacitance. And this is our oxide capacitance. And the region between the depletion and the inversion, actually there's still a little bit transition here. This is the region we call as a weak inversion. And compared to the weak inversion, so we can also call this region as a strong inversion. So that's a completely picture for the CV characteristic from the negative to the positive bias that we'll experience from the accumulation, depletion, and then the inversion. So therefore, one thing want to mention that this is considered as a low frequency capacitance with a p-type substrate. And then the details of the CV curve can be considered C capacitance versus voltage. So we have this accumulation and depletion, weak inversion, strong inversion. So this one will be equal to the oxide capacitance. This is region of the accumulation. And this is the region we call as a depletion. And this is the region strong inversion, and also the weak inversion. And the point between the weak inversion and the depletion will have this reach for the C minima. And also the point between the accumulation and depletion is a point related to the flat band voltage and also the flat band capacitance. Somewhere there. The Cx, this is also the Cx, can be estimated from X zone S over Tx. And since we consider this is a low frequency, which means that there could be the difference under the different frequency. And if we consider frequency effects, there's something we have to be careful. There are two sources of electrons that can change the charge density of inversion layer. The first one is diffusion of minority carrier electrons from the p-type substrate across the space charge region. Another one is the thermal generation of electron hole pairs within the space charge region. So both of these processes generate electrons at a particular rate, and the electron concentration in the inversion layer then cannot change instantaneously. So which means that ideally we have this dq increase, but under the high frequency, this additional dq prong cannot be reflected in this region because of this charge cannot respond. In the very limited high frequency, the inversion layer charge will not respond to a differential change in the capacitance voltage. So therefore, the dq prong won't reflect at this region at a high frequency. The differential change in the charge occurs at the metal and in the space charge width in the semiconductor. So therefore, this dq prong will reflect at the end of the depletion width under the high frequency consideration. So So therefore, with taking into account these frequency effects, we need to a little bit revise our CV curve. At a high frequency, under the inversion bias, the capacitor now is become as a series of C arcs in series with CSD again. So therefore, the inversion capacitance at the high frequency is equal to 1 over C arcs. But now also have to take into account the depletion width. So again, plot the CV characteristic. At the low frequency, we have the accumulation, depletion, inversion. This is case under the low frequency. But at the high frequency, the inversion charge cannot respond, and therefore at a high frequency we will see the CV curve is shown here. So that's the main difference between the low frequency and then the high frequency. So that's a one non-ideal effect. Another one we have to take into account is a fixed oxide interface charging effect. So in the previous, when we take into account the flat band voltage, we already consider that there is a QSS happening in the dielectric. And this fixed oxide charge will also in the end influence our flat band voltage and threshold voltage. So this is a one idea. For example, if we have the higher QSS, it's become higher and higher, then we will see our CV curve will shift to the left here. So the flat band voltage shift to more negative bias, not to more negative voltage for a positive. Oxide charge. And the CV characteristic can be used. Therefore, we can use the CV to determine the equilibrium fixed oxide charge. So that's become very useful tool for us, because normally we would be very interested to understand how much these fixed oxide charges in our MOS transistor or MOS capacitance. So we can use this equation to analyze and to see that the equilibrium fixed oxide charge. Another very important issue is the interface charge effects. So, as I already said, that if you look at the band diagram, and then if we try to have the dielectric here, so this is an energy band diagram for semiconductor at the oxide semiconductor interface. And because as we knew that the periodic nature of semiconductor is terminated at the interface, semiconductor will be terminated at this interface, and therefore the allowed and electron energy level will exist with this forbidden band gap. This is the same concept that we have been illustrated. Once we talk about in the previous we talked about metal semiconductor, we already mentioned that it is possible to have this allowed electronics interface state here. And then these allowed state are referred to as an interface state. And the charge can flow to between the semiconductor and then an interface state. So for example, once we have electrons in this interface, the electron can be flow and captured by this interface state, and that's we call as this will lead to the electron trapping. And again, if we have the holes, and then the hole will also flow to this allow energy state, that will cause as a hole trapping. So in anyhow, the charge can flow between the semiconductor interface state. That will lead to the issue of the trapping. And that's become one of the key issue for reliability. So this is also something very crucial that when we talk about the MOS. So here is some more analysis related to this interface state. So by consider interface state, we can define the two different kind of the state here. One is called the acceptor state. One is called the donor state. So the acceptor state exists in the upper half of the band gap, and donor state exists in the lower of the band gap. And there's a clearly definition for the acceptor and donor. So acceptor means that it's neutral if Fermi level is below the state, which is this one. This is acceptor state. So when this is our state, and the state is neutral if this state is if the Fermi level is below the state. So this is our Fermi level. This one below our state. So therefore there's no any charging effect. So this will be the neutral. But however, this will become negative charge if the Fermi level is above the state. So once our Fermi level is above this state, then we start to see the negative charge here. So if we see the charge state has this kind of the characteristic, we call this as an acceptor state. On the other hand, we call it a donor state. A donor state is if a Fermi level is above the state, that will cause a neutral. So it's like this one. If a state, this one. If the Fermi level is above the state, and this will have any charge, so that will have the neutral. But however, become positive charge if the Fermi level is below the state. If the state is above the Fermi level, that will cause a positive charge. That's what we call the donor state here. The charge of the interface state is a function of the gate voltage applied across the MOS capacitance. So anyhow, this one is here, this one is here. So anyhow, when we talk about interface state, you should remember that there is two different kind of state. One is acceptor, one is a donor, and this acceptor and donor will cause a different kind of the charging characteristic. So to give us a more sense how this reflect to our IDVG characteristic, so let's just make us a quick example. Most of the textbook, when you talk about this, they will just stop here, and then you will get so confused that how this in the end to influence the characteristic and why this is important. So therefore, we will use one typical IV to illustrate this characteristic. So if you have a one IDVG, this is typical IDVG that has a VTH here. But now if we have the negative charge in the acceptor state, that will cause completely shift of the right of the IDVG characteristic, because now you have a negative charge there. So negative charge will cause you need a little bit further high bias to turn on the transistor. So this is because of the negative charge in the acceptor state. And that also can be considered as electron trapping. So that's why we define as the acceptor state, because in the end we hope to understand why at a certain case our IV curve will shift to the right, and then what kind of state trapping will influence. So therefore, by using this definition, we understand this can be a acceptor state that causes electron trapping. And there's also possible that we will see our IV curve shift to the left, and this because due to the positive charge in the donor state. And that's because due to the hole trapping. So this trapping in the acceptor and then the donor in the end will always lead to the influence on our IV characteristic, because our IV characteristic is a shift. That means we start to have this reliability, because that will not fit our original design. Our original design could be threshold voltage at 1 volt, but now you see your threshold voltage become 2 volt, or your threshold voltage become 0 volt. Anyhow, if this doesn't fit our original design, that's always considered as a reliability issues. So we can also use this as an additional consideration. We can use a band diagram to understand as well. So this is a case, for example, if you're under the minus VG, this is minus VG, then you start to see these positive donors will influence. And because this is a case of a Fermi level below our trap state, our EF smaller than ET, And if we consider at the inversion, that's positive VG, then we will start to see the impact coming from these acceptors, because right now this is a condition that the EF larger than ET. And also this interface state will become the stretch for our CV curve. So that's very often to see the original is a red one, but the dash one is a one with a CV, with the interface state influence. Okay, so today we will stop here, and then we will, because the next one is related to MOSFET operation, it will be better to finish at one time.